We have just seen that rough hydrophobic materials can efficiently repel water. But here is a completely different situation in which, however, we observe similar behaviors. This peculiar wetting, or rather non-wetting state, is observed when water is poured on a hot, very hot metallic plate, or when liquid nitrogen at about minus 200 degrees is spilled on a table. In both cases, the liquid splits into numerous elusive spherical drops that do not evaporate readily despite the large temperature of the substrate. Water droplets are dispensed from a pipette on a copper plate brought at 300 degrees. The drops rebound, move rapidly, bounce on the side walls, merge into bigger drops. Even if the temperature of copper is way above the boiling point of water, evaporation is slow, and the lifetime of the drops can be on the order of minutes. This remarkable behavior appears at a temperature called the Leidenfrost temperature, named after the German physician Johann Leidenfrost, who described it in 1756. How can we explain the Leidenfrost phenomenon? We get the answer by looking at the drops from the side. Then, we can see that they meet the substrate with a large angle. Looking even more carefully, we notice the thin dark line between the bottom of the drop and its reflection on the substrate, which evidences the existence of a vapor film that prevents a direct contact between the liquid and its hot substrate. Vapor prevents boiling, and it thermally insulates the liquid, which explains the long lifetime. In addition, levitation on vapor generates a purely non-wetting situation with a quick dynamics associated to such states.
A further evidence of the vapor film between the liquid and the solid is provided by looking at a puddle of water several centimeters across. The puddle fluctuates quite rapidly, but at regular intervals, a gas bubble grows and creates a bulge in the middle of the liquid. This is a result of the instability of the bottom liquid-gas interface, since the lighter phase, the vapor, tends to rise in a denser one, the liquid. This instability is opposed by surface tension, which explains why we only observe the chimney of vapor at large puddle size. We have seen that Leidenfrost drops are supported by a thin vapor film underneath the drop. But now we would like to understand in more detail how the thickness of this vapor film is determined. So our question is, what is the thickness of the film? So we'll sketch here a Leidenfrost drop. This is the hot substrate at a temperature Ts. And this is a drop, and I will consider a drop which is typically centimetric in size. So it's essentially flattened by gravity. And I do this because the calculation will be easier in this case. So R is the radius of the drop. It is slightly larger than the capillary length. And as a consequence, since the drop is non-wetting, the thickness of the drop, H, is simply twice the capillary length. Now my question is, what is the thickness of the vapor film here, which I will call epsilon, given the size of the drop and also given the temperature difference between the substrate and the bottom of the drop, which actually is at the boiling temperature, Tb. So I will characterize this by the temperature difference, delta T, which is the temperature of the substrate minus the boiling temperature of the liquid. Now, if I sketch the region in the film on a larger drawing, what I'll see is the substrate, the solid substrate, and the liquid air interface. And I have vapor coming out of this interface at a typical velocity v. And the vapor has to escape underneath the drop at a velocity which I will call u. It is different of v because of the aspect ratio. Now, the drop is supported by the film because due to this flow, there is a difference of pressure between the outside of the drop and the inside of the film. And this pressure difference, delta P, is given by the Stokes equation for the motion of fluid. The Stokes equation is such that the viscosity of the vapor, eta, multiplied by this velocity u, and divided by the thickness of the film squared, this is epsilon, is balanced by the pressure gradient, by the difference of pressure delta P between the inside of the film and the outside, divided by the typical size of the drop r. Now, I have also to take into account the mass balance, that is the flux of vapor, which is typically V multiplied by the surface of the drop, which is pi r squared, has to be equal to the radial flux, which is 2 pi r times epsilon times u. So u is typically proportional to v multiplied by r over epsilon. U is larger than v by a ratio which is the aspect ratio. As a result, I can write the force acting on the drop from underneath, so that the force due to the vapor film. And this force is essentially the pressure difference integrated over the whole surface of the drop. So this force is delta P multiplied by r squared, which is typically eta times u times r cubed divided by epsilon squared. Now, if I then take into account this result, I can write that the force due to the vapor is eta v times r to the fourth power divided by epsilon cubed. Now, in order for the drop to be in mechanical equilibrium, this force due to the vapor film must balance the weight of the drop. And the weight of the drop is the density of the liquid, rho L, multiplied by the volume, which is proportional to the radius to the square, multiplied by the thickness h. So this is our mechanical balance for the drop. Now, in order to go further in the computation, we will need to link this velocity v to the heat flux underneath the drop. So now we turn to the heat flux from the drop. I will keep only this result. So the heat flux, which I will call Q, is given by Fourier's law. It's given by the temperature gradient in the vapor film, which is delta T divided by epsilon, multiplied by the thermal conductivity of the vapor, which I will call lambda, and multiplied by the area of the film, which is proportional to r squared. But I can write the heat flux in a different way by saying that the heat flux is the flux of mass, dm divided by dt, multiplied by the latent heat of evaporation, L. And the mass flux is simply the density of vapor, rho v, multiplied by the velocity v, integrated over the area of the drop, which is v times r squared, and again multiplied by L. So by comparing the two definitions of the heat flux, I can derive the value of the velocity v, which is proportional to lambda delta t, divided by epsilon rho v L. And so we have determined the value of the velocity v of the vapor, and we will use this value into the formula giving us the force due to the vapor. And I'm going to use this value of v into this, so that the force due to the vapor is the viscosity eta multiplied by lambda delta t divided by rho v L times epsilon to the fourth power multiplied by R to the fourth power. And this is balanced by the weight of the drop, which is rho L multiplied by R squared multiplied by H. So from this, I get a value for the film thickness epsilon, which is the result I wanted to get. And epsilon is given by eta lambda delta t divided by rho v rho L H capital L and multiplied by R to the fourth power, and this is to the this is R squared multiplied to the 1/4 power. And I can actually rewrite this result in a simpler manner. I can write this as a length b multiplied by a length r, and this product being at the power 1/2. B is indeed a length, and it incorporates all these physical parameters. And if I take the value of these parameters, I find that B is typically 1 micron, that is 10 minus 6 meters, and R is typically 1 centimeter, that is 10 to the minus 2 meters. And as a result, epsilon is 10 to the minus 4 meters, that is 100 microns. So this is the typical value of the thickness of the vapor film under a centrometric drop. And this value is such that it is still visible to the naked eye. This is the smallest length that we can perceive with the naked eye. And this is why Leidenfrost was able to see the vapor film just with his eyes. Now, another remark is that, as you can see, the thickness of the film is proportional to the square root of the drop size. Epsilon is proportional to the square root of R. And this might seem paradoxical at first sight, because as the drop grows bigger, its weight increases, and we could think that because of this increased weight, the thickness of the vapor film would diminish to support this. But as the vapor flux also increases with R squared, the result is such that as the drop grows, the thickness of the film indeed becomes larger, which is not obvious at first sight. Now, a final thing that we can get from this calculation is the mass flux of vapor. The mass flux of vapor, dm divided by dt, is such that it is proportional to lambda delta t R squared divided by epsilon L. And once we know epsilon, we can compute it. And typically for a centrometric drop with a difference in temperature, which would be 200 degrees C, what we find is that the mass flux is typically 1 milligram per second. So if we have a drop which will have a mass of typically 1 gram, we understand that this drop will evaporate over a time scale which would be typically hundreds to thousands of seconds. This is several minutes, and this is indeed what we observe in the experiments. These centrometric Leidenfrost drops can stay on the hot plate for several minutes. The thickness of the vapor layer is such that it decreases considerably the heat flux between the drop and the solid compared to a direct contact. This is a major problem when one needs to cool rapidly hot solids such as metal plates. Using a spray of salted water drops is proved efficient because salt grains promote the contact between water and solid, which enhances the heat flux. In the same vein, using rough substrates will often destroy the Leidenfrost state, or to say more precisely, will shift markedly the Leidenfrost temperature to much higher values. Conversely, using superhydrophobic materials allows one to lower the Leidenfrost temperature down to values close to the boiling point of water. This is seen in this experiment where we looked at a so-called inverse Leidenfrost situation where a hot solid is immersed in water, an experiment first performed by Faraday. One of the spheres is just made of steel, while the second one is coated by hydrophobic textures. One of the spheres is just made of steel, while the second one is coated by hydrophobic textures. The spheres cool down as a function of time, and when the Leidenfrost point is crossed, we observe for the hydrophilic sphere only a sudden and explosive boiling. In contrast, the transition between the Leidenfrost state and the Cassis state is found to be continuous on the superhydrophobic sphere.
Leidenfrost drops are amazingly mobile owing to the cushion of vapor on which they levitate. This implies that even tiny forces can propel them at significant velocities. This property is made spectacular when looking at the behavior of water on hot ratchets. The liquid does not only levitate, but it also self-propels in a well-defined direction with a well-defined velocity. This experiment was understood by considering that the flow of vapor beneath the drop is rectified by the asymmetric scales. Vapor mainly flows down the teeth, which drags by viscosity the liquid above. But there is more. A Leidenfrost droplet placed at rest on a strictly horizontal substrate can host an asymmetric internal flow. The flow itself might be due to temperature gradients inside the drop and its asymmetry caused by confinement. As the drop evaporates, it eventually detaches from the needle holding it, and this kind of wheel is found to move in the direction suggested by rotation, despite the absence of contact with the substrate. Hence, the celebrated mobility of Leidenfrost drops is found to be intrinsic.